All right, everybody. So we're working on our exponential functions here, and we've got a couple problems that I wanted to go over. The first one is just looking at growth and decay. So meaning you're either getting bigger over time or you're getting smaller over time, and the rate of change is multiplication. So you're not adding the same amount or subtracting the same amount, but you're multiplying by the same factor every time. So here's our situation. We've got 24 cases uh, here at the beginning, and then 5 weeks after that, we've got an exponential growth. So you see that familiar looking curve there. And whenever you have an exponential problem, remember that we're talking about a situation where you're always multiplying by the same amount. So you started with 24 things and you multiplied it by something to end up with 36. And the way you solve an equation with multiplication is you divide. And it turns out that 36 divided by 24 is 1.5. So that's the amount that we're multiplying by. So I know that answer choice A here, because it's asking us to find an equation for the number of cases X weeks later. I know answer choice A can't be right because this would mean you have 12 times as many cases. That's not what's going on. We didn't go from 24 cases to 24 times 12 cases. You might think that 12 is the rate of change because 36 minus 24 is 12, but that's thinking of it like a straight line. We're not going in a straight line. We're going at an exponential curve. This one right here, it multiplies 24 times 1.5. And if you do, 24 times 1.5 gives you 36. But this one does not have an exponent. It just has an x right there as a line. So that pattern would go, if I make a little table here, if I plug in x equals 0, I get 0 cases. If I plug in x equals 1, I have 36 cases. X equals 2 is 72 cases. None of that matches up with what we're seeing on the graph, with the exception of 1 and 36. So it meets at one point. That would be a line going like this. Okay. This one right here is a linear one that goes 12 more cases each day. So that one would start at 24 and would go like this, but it's also not going to capture the amount. Only answer choice D matches that you start with 24 and you get 1.5 times as many cases the next week. By the way, I want to remind you that this can be thought of as a 50% increase. So you've really got to get fluent at looking at what your multiplying factor is and thinking of it as a rate of increase or decrease. So just keep practicing that. Okay, if the trend continued, would the number of cases be greater than 300 after 5 weeks? So we can go 24 times 1.5 raised to the 5th power. This is probably going to be a real big number. Let's see what ends up happening. Okay, so I typed it in. Honestly, not quite as big as I thought it would be, but still pretty big. So we end up with 182.25. That's smaller than 300. So the answer is no. And that's it for that first one. Now we're looking at when we don't have whole numbers as our exponents, but now we can have fractions or decimals as our exponents. And that's kind of the new shift in these most recent lessons. So we're talking about medication for treating treating fleas in dogs. And it tells us here that it's exponentially, so we know we're multiplying it. And it decreases by half each week. So I know that my R is 1 minus 0.5, or it just turns out to be the same as 0.5. The reason I showed you the 1 minus 0.5 is because if I told you it decays by a tenth, that doesn't mean you multiply by 0.1. That means you multiply by 0.9. Where did I get 0.9 from? Well, that's just 1 minus a tenth, meaning 0.9 is remaining. On this particular problem, it doesn't matter because if you lose half of it, you've still got half left over. But I just wanted to remind you that we're going always related back to 100%. Okay. So find the amount of the medication in 1 week, 2 weeks, and 3 weeks after it's administered. So we start with 4. It's half as big to the 1 week. Then we have 4 half as big to the 2 weeks. Then we have 4 half as big to 3 weeks, like that. And this is just typing it into your calculator. You could also just do it in stages because it's not too hard to do 4 times a half and then taking the answer you just got times a half, taking the answer you just got times a half. But sometimes the numbers aren't quite so nice and you want to use the formula to see that it comes out to be the same thing right there, 0.5. Write an expression, number 2, write an expression to represent the amount of medication 1 day after it's administered. Well, I know that we can go 4 times 0.5 to the number of weeks, but that doesn't work for days. So what we can do is we can change this into 4 times 0.5 to the number of weeks divided by 7. Because 1 day, sorry, I shouldn't have the variable w there. I should have the number 1. Because 1 day is 1/7 of a week. Okay? And if I type that in here, think about what kind of a number should you expect. Not that much has really decayed. There's still about 3.6 remaining in there. Okay. And the last one on this particular exit ticket, explain what f of 4/7 means. Well, f of 4/7 would mean 4 times 0.5 raised to the 4/7. That would mean 4 days after administration. So after the medicine was administered, this is going to be the amount remaining. So sorry about my handwriting there. The amount remaining 4 days after the medication was administered. So let me know if you got questions about those problems on the exit ticket. It's important that we know how to do those because we're going to keep rolling through this stuff and you got to keep up on top of it.